This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
The standard model of physics describes a microscopic reality governed by probabilistic chance. At the lowest levels, we model the universe as a chaotic swarm of point particles, defined by uncertainty and disjointed interactions. We build our most critical systems, cryptographic ledgers, energy grids, and civilizational infrastructure, on top of this foundation. We expect macroscopic stability from a system whose root physical laws allow for inherent randomness. This creates an engineering ceiling. It is impossible to achieve absolute failsafe determinism in a macroscopic system if the microscopic model at the root allows for random state changes. State-level planners require absolute determinism. Managing a civilization requires unbroken data provenance and operational stability that remains consistent whether observing a single computational node or an entire continental supply chain. Resolving this vulnerability requires a unifying ontology where the foundational physics engine inherently generates macroscopic stability as a property of its own laws. Fractal Quanta Theory, or FQPT-Q, functions as an executable, deployable physics framework designed to serve as an operating system. In this model, reality is driven by invariant-preserving topology and observer-resolved excitations. Everything that exists is a specific measurable perturbation within a continuous field. This schematic outlines how the framework operates as a master integration layer. It brings quantum topology, emergent gravity, and cryptographic governance together under a single mathematical proof. We call this the delta core integration. Because the mathematical proofs are recursive, the invariant properties of a single quantum interaction are preserved as they propagate across the system. This allows microscopic laws to govern macroscopic grids without the loss of state integrity. By unifying these scales, FQPT-Q provides the physical bedrock required to deploy sovereign intelligence systems that remain aligned under all transformations. In FQPT-Q, quanta are defined as observer-resolved, localized excitations within a continuous field. They are stable, measurable ripples in the substrate of reality. The behavior of these field excitations is dictated by a specific mathematical language known as Braid algebra. Under Braid algebra, interactions are strictly non-commutative. The exact order dictates the outcome, leaving a permanent trace. Over time, these interactions mathematically close in on themselves, forming stable topological knots. These knots are what human instruments classify as particles. Standard quantum mechanics treats subatomic behavior as a calculation of probabilities. This topological model dictates that knot formation is permanent, sequential, and deterministic. At its lowest operational level, FQPT-Q replaces probability with a mathematically stable, fully auditable topological history. To understand how these topological knots form a universe, we must look at the background architecture that houses them, the KP field. When thousands of these stable quanta knots move and interact within the KP field, they flow together, creating distinct currents of structural density. This density flow reveals a specific property of the KP field equations. Gravity is not an independent force. Gravity emerges as a macroscopic curvature caused by the density and flow of quanta. As knot concentration increases, the underlying field warps. Viewed at scale, this resulting curvature matches the exact geometry predicted by general relativity. Unifying the quantum scale with the cosmological scale confirms that the physics engine is stable enough to support planetary engineering. Mathematical topology is only useful for sovereign infrastructure if it can be verified in the physical world. The framework requires empirical grounding. We execute this verification through the Reality Bridge protocol. This is an adversarial, blind testing environment designed to subject the theory to strict falsifiability. The protocol runs mathematical simulations side by side against physical signal readouts. Left, the theoretical descent curve. Right, physical telemetry. Auditors analyze both streams to locate invariant matches, quantitative signatures aligning across pure mathematics and raw physical data. These matches occur without the need for statistical smoothing or approximations, demonstrating that the framework exhibits strict cross-domain reproducibility. FQPT-Q stands as a universally verifiable system, prepared for digital translation. With the physics validated, the next step is operationalizing this truth into secure digital infrastructure. This takes place within CodexStation, an execution environment that anchors physical telemetry directly to a cryptographic